Zeno's Dichotomy Paradox. Zeno's Dichotomy Paradox says that to reach any goal, you must first cover half the distance, then half of what's left, and so on. This leads to an infinite series of steps, suggesting you can never finish moving forward. In reality, we do complete journeys, but thinking of movement as endless halves makes it seem impossible. The paradox comes from treating an ongoing action like motion as if it were broken into an infinite number of tiny, separate tasks. Achilles and the Tortoise. Achilles and the Tortoise is another of Zeno's ideas. Achilles, who runs fast, gives a slower tortoise a head start. To catch it, he must first get to where the tortoise was. By then, the tortoise has moved forward. Achilles keeps closing the gap, but each time the tortoise moves a bit further. This suggests he never catches up. Of course, we know faster runners do pass slower ones. The paradox appears because it breaks motion into an endless number of steps. Sorites Paradox, the heap paradox. The Sorites Paradox asks, if you have a heap of sand and remove grains one by one, when does it stop being a heap? Removing one grain doesn't suddenly change a heap into a non-heap, but if you keep going, you'll have almost no sand left. This challenges how we define vague words like heap. There seems to be no exact line between a heap and not a heap, making it hard to set a clear boundary. The Ship of Theseus. The Ship of Theseus asks if something that has all its parts replaced is still the same thing. Imagine an old ship. Over time, you replace each plank and nail until none of the original parts remain. Is it still the same ship? This makes us wonder if identity depends on physical components or on some continuous existence. The paradox highlights how tricky it is to define what makes something itself over time. The Liar Paradox. The Liar Paradox is a statement like, I am lying right now. If that's true, then you are lying, so it cannot be true. If it's false, then you are telling the truth, making it true. This creates a loop with no clear answer. The paradox shows that self-referential statements can break simple notions of truth and falsehood, making language and logic seem tangled. Russell's Paradox. Russell's Paradox involves the idea of a set containing all sets that do not include themselves. If this special set exists, does it include itself? If it does, it breaks its own rule. If it doesn't, then by definition it should. This logical puzzle forced mathematicians to rethink the foundations of set theory. It shows that certain ways of defining collections lead to contradictions. The Grandfather Paradox. The Grandfather Paradox is about time travel. If you go back and prevent your grandfather from meeting your grandmother, you would never be born. If you were never born, you couldn't have traveled back. This suggests that changing the past might be impossible or that timelines can't work in a simple, linear way. It highlights deep confusion about cause, effect, and the flow of time. The Barber Paradox. The Barber Paradox describes a barber who shaves all men who don't shave themselves, and only those men. If the barber shaves himself, he shouldn't. If he doesn't shave himself, he should. Either choice breaks the rule. Like Russell's paradox, it shows how certain self-referential definitions cause logical loops with no consistent solution. The Unexpected Hanging Paradox. In the Unexpected Hanging Paradox, a judge tells a prisoner he will be hanged on a weekday and it will be a surprise. The prisoner reasons that it can't happen on the last possible day because then he would expect it. Working backward, he eliminates every day and thinks the hanging can't be a surprise at all. Yet the hangman still manages to surprise him. This paradox questions our understanding of knowledge, prediction, and what makes something a surprise. Schrodinger's Cat Paradox. Schrodinger's cat is a thought experiment in quantum physics. A cat is placed in a box with a device that can randomly kill it. Until checked, quantum rules say the cat can be thought of as both alive and dead. Opening the box decides its fate. This paradox shows how observing something might affect what it is, challenging the idea that reality exists in a definite state without us looking. The Pinocchio Paradox. Pinocchio's nose grows if he lies. If Pinocchio says, "My nose will grow now," what happens? If this is true, then he isn't lying, so his nose shouldn't grow. If it's false, then he is lying, and his nose should grow, making it true. This is similar to the Liar Paradox, but uses a fairy tale character's special property to show how tricky self-referential statements can be. The Omnipotence Paradox. The Omnipotence Paradox asks if an all-powerful being could make a task it can't do, like a stone so heavy it can't lift it. If it can, it's not all-powerful because it can't lift the stone. If it can't, it's also not all-powerful because it can't create the stone. The paradox questions the idea of unlimited power, and whether such a concept makes logical sense. The Boy or Girl Paradox. The Boy or Girl Paradox deals with knowing a family has 2 children and at least one is a boy. What is the chance the other child is a girl? The answer depends on how the information is given and can seem confusing. It shows how tricky reasoning about probability can be when we don't carefully define conditions. It's not just 50-50 once details change. Galileos Paradox. Galileos Paradox notes that there are as many square numbers, 1, 4, 9, 16, as there are regular counting numbers, 1, 2, 3, 4. Intuition says there should be fewer squares than all numbers, but there's a 1-to-1 match. Each number has a square. This challenges how we think about infinity. Even though squares are a subset, infinite sets can match each other in size. Nukes Paradox. Nukes Paradox involves choosing between two boxes, one transparent with a known small amount of money, and one opaque with potentially a large amount. A predictor has already guessed your choice. Do you trust the prediction and choose just the opaque box, or hedge your bets by taking both? The paradox challenges ideas about free will, prediction, and rational decision-making. Different logical approaches lead to different best strategies. The Lottery Paradox. The Lottery Paradox says you can reasonably believe every single lottery ticket will lose since each has a tiny chance of winning. But since one ticket must win, it's not reasonable to believe they all will lose. This shows that combining individually reasonable beliefs can lead to an overall contradiction. It highlights problems in how we handle uncertainty and collection of assumptions. Simpsons Paradox. Simpsons Paradox shows that a trend appearing in different groups of data can disappear or even reverse when the groups are combined. For example, a treatment might look good in separate groups, but worse overall when the groups merge. It teaches us that how we split or combine data changes what we conclude. It warns against making quick judgments without considering how data is organized. The Fermi Paradox. The Fermi Paradox asks, if the universe is huge and old and there should be many advanced alien civilizations, why haven't we found any sign of them? With so many stars and planets, life seems likely. Yet space seems quiet. This makes us wonder if life is rarer than we think, if aliens are hiding, or if we're just not looking in the right way. It's a puzzle about expectation versus observation. The Monty Hall Problem. The Monty Hall Problem is about a game show with 3 doors. One has a prize, 2 do not. You pick a door. The host, who knows where the prize is, opens a different door showing no prize. Should you switch to the remaining door or stay? Surprisingly, switching doubles your chances of winning. Many people find this result confusing. The paradox-like puzzle shows that probability and intuition don't always agree. The Abilene Paradox. The Abilene Paradox describes a group deciding on something that nobody really wants because each person thinks the others want it. Everyone stays silent to avoid conflict, leading to a choice no one likes. This paradox shows how poor communication and assumptions about others' desires can cause groups to make decisions that don't reflect anyone's true wishes. The Friendship Paradox. The Friendship Paradox says that your friends usually have more friends than you do. This sounds odd, but popular people are more likely to be your friends, raising the average number of friends your friends have. It's a reminder that your personal experience in a network can be biased by who you are connected to, revealing that our social views can be skewed by statistics. Brace's Paradox. Brace's Paradox says adding an extra road to a traffic network can cause even more congestion, making travel times worse. Removing a road can sometimes improve traffic flow. This is counterintuitive because we usually assume more roads help. But if everyone chooses what they think is the fastest route, the system as a whole can become less efficient. It shows that more options don't always mean a better outcome. The Bonaktari Paradox. The Bonaktari Paradox says a solid ball can be split into a few strange, carefully chosen pieces and rearranged into 2 balls of the same size as the original. This seems impossible as it violates common sense about volume. However, it relies on advanced mathematics dealing with infinite sets and doesn't apply to real physical objects. It shows that math can produce results that conflict with our everyday intuition. The Infinite Monkey Theorem. The Infinite Monkey Theorem says that if a monkey hit keys at random on a typewriter for infinite time, it would almost surely type any given text, like Shakespeare's works. Though unimaginably unlikely in any finite stretch, given infinite time, even the rarest event can happen. This paradox challenges our grasp of probability and reminds us that, given unlimited chances, even something that seems impossible can occur. If you enjoyed the video, subscribe for more.